In the timeline of commercial aviation, progress reached a plateau 20 years ago. Since the retirement of the Concord in 2003, commercial flight speeds have remained frozen in place. While the Concord was an engineering achievement, it faced severe operational limits. It consumed massive amounts of fuel, its route economics were narrow, and it generated sonic booms loud enough to shatter windows on the ground. The financial strain became unsustainable following the Air France crash in 2000. That tragedy broke public trust in the airframe, making it impossible for airlines to justify the aircraft's mounting operational debts. To manage the noise impact, the United States banned all overland supersonic flight in 1973. By restricting these aircraft to ocean crossings, regulations capped the potential market for high-speed travel and kept commercial aviation in the subsonic range for half a century. That 50-year speed limit was lifted in June of 2025. A presidential executive order repealed the overland ban, replacing rigid speed limits with a noise-based standard. If an aircraft can fly quietly, it is permitted to fly at supersonic speeds over land. Physical proof of this shift arrived recently when the Boom XB1 demonstrator became the first independently developed civilian aircraft to successfully break the sound barrier. Supersonic flight is legally and mechanically viable again, but to sustain operations, modern engineers must solve three specific mandates: speed without the sonic boom, absolute safety, and a net zero environmental impact. This diagram shows the physics of a traditional sonic boom. As a supersonic aircraft pushes through the air, individual pressure shock waves merge. When they hit the ground, they create a single energy spike, the destructive crack heard at ground level. NASA's X-59 uses a 38-foot narrow nose to physically manipulate these waves. This elongated geometry forces the shock waves to stay separated, preventing them from merging. Because the waves never combine, the violent boom is reduced to a sonic thump. On the ground, the sound is roughly equivalent to a car door slamming. This design is now being validated outside of simulations. The X-59 has transitioned into active runway testing in the California desert. By mastering the physical geometry of sound, engineers have addressed the primary acoustic barrier that once made overland routes politically impossible. However, that needle nose design creates a new safety challenge. The X-59's nose is so long and slender that it completely blocks the pilot's forward visibility. To fix this, engineers removed the front window. In its place, the external vision system uses cameras to render a hyperfluid, ultra-clear digital view of the sky directly onto a cockpit display. Operating this system at Mach speeds requires immense computing power. Specialized GPU modules process high-bandwidth camera data with zero latency to keep the pilot oriented. These digital systems are tightly integrated into the experimental jet's airframe, replacing traditional glass with high-speed processors. Modern supersonic design trades mechanical visibility for high-speed digital processing. This shift allows the aircraft to maintain its specialized aerodynamic shape without compromising pilot safety. Then there is the matter of fuel. Flying at Mach speeds burns 5 to 7 times more fuel per passenger than standard subsonic flights. To combat this, manufacturers are using advanced materials. Replacing aerospace metals with multi-walled carbon nanotubes and composites reduces the aircraft's weight by up to 50%, lowering the energy required for flight. Thermal efficiency is also critical. As friction heats the wing's exterior, recirculating fuel lines absorb that heat and carry it back into the fuselage, using the fuel itself as a cooling mechanism. By combining weight reduction and thermal management with 100% sustainable aviation fuel, the industry is working to uncouple high-speed travel from its historical environmental impact. This technology is now transitioning from experimental flight tests into a touristial business. Major carriers like United Airlines have already placed orders for supersonic jets intended to cut transatlantic flight times in half. Look at how the network feasibility changes. Previously, routes were confined to ocean crossings, but with the overland ban lifted and new acoustic models in place, the map of profitable global routes rapidly expands across every continent. The industrial scale is already visible. Aviation's superfactories are now building the assembly lines required to manufacture these aircraft by the dozens. We are on the verge of halving global travel times. By prioritizing acoustics, digital safety, and sustainable materials, this return to high-speed flight can proceed without leaving shattered windows or a damaged ozone layer behind.